Okay. So Hiro, are you ready?
Yeah, sure.
Okay. Hi everyone. It's 1:30 now, so I think we'll go ahead and start. This time, despite the fact that the slides say Graham Neubig, it's actually me together with Hiro Hayashi, the one of the TAs, and we'll be talking about learning from and for knowledge bases. So how can we intersect learning neural networks together with the knowledge that's included, symbolic knowledge that's included in knowledge bases. And Hiro is doing some work on this topic, so I think he's a good person to take over half of the class today. So without further ado, I'll turn it over to Hiro.
Cool, thanks for the introduction. So in this lecture, we would like to talk about, as Graham mentioned, intersection of neural NLP models and knowledge bases. Okay, so what typical knowledge bases look like is they have two elements. So structured knowledge bases contain, first of all, entities and relations. In the brackets next to the names, there's like a graph way of representing it, but knowledge bases doesn't necessarily be in the graph form. It just happens that reason like RDF triples or most popular kind of knowledge bases tend to be graph format. So I think knowledge base, the word knowledge base and knowledge graph is used kind of, they are used interchangeably. So in this graph format, entities are represented as nodes on the graph typically, and relations are the edges that connect between the entities. And in this lecture today, we want to ask, in general, in NLP, using knowledge base, there are several questions to ask. So first of all, given a large scale knowledge base, how can we, well, first of all, given some information, how can we construct this kind of structured database? Another question to ask is, once we construct or if we use some existing knowledge base, how can we use those information to improve the performance of NLP models or improve the neural representations that can be later used for NLP tasks. And optionally, I will also briefly mention about how knowledge bases are useful for question answering. So to begin with, I'd like to cover some of the famous knowledge bases historically proposed. I guess a lot of people are familiar with this name, WordNet. It's a type of knowledge base that contains semantic relationships between words. So each node, they are not like existing real word entities, but rather they are words, a lexicon. And the connections are in different forms based on different part of speech tag assigned to each word. So for nouns, there is a relation. As you can see there, well, you can't really see, but hatchback and car is a relation connected. They're also part of a relationship and some type instant distinctions. There are also verb relations. So the words can be also verb, they're connected. And interesting relations that connect between two verbs are specificity-based hierarchy, basically. And yeah, there are also antonymy described in this WordNet database. And historically, these WordNet knowledge base was incorporated into learning better word embeddings that take into account these semantic relationships, or as well as the construction of data sets for semantic similarity evaluation. So why can we do semantic similarity evaluation using WordNet? It's because if you look at the central part of the graph, where motor vehicle has three children, motor car and go-kart truck, these three words in the same level of depth in the graph can be considered as synonyms, and that helps a construction of semantic similarity evaluation datasets. So the next database that is also pretty classic, and nowadays I don't think people hear a lot about this database. It's called Psych or Psych project. And Psych is basically a database of common sense knowledge. So unlike real world entity relational facts, like the capital of the United States is Washington, D.C., they attempt to represent and express common sense knowledge, focusing on more like skills or how some kind of knowledge that is hard to explain in the simple sentence. So examples in this hierarchy you can see is like organization, agents, actions, plans, goals, things like that. According to some other sources that I read, these kind of implicit knowledge or common sense knowledge include something like how to speak a certain language, which obviously you can't express in a single sentence. And that contrasts to relational facts that we will see later, which is called explicit knowledge. And nowadays, Psych is, I think, I don't even see a lot of people citing Psych recently. I don't think it's been pretty, I think the kind of knowledge that they handle is pretty hard to incorporate into even in the most modern systems. They are expressed in higher order logic. So if you can take advantage of this resource and make some very nice AI system, that would be great. The next thing I want to talk about, the next two things I would like to talk about are, in contrast to common sense knowledge, they are called explicit knowledge, where it basically talks about relational facts between two entities. So one project and a very large scale database that's freely available is called DBpedia. And you can think of DBpedia as like database form of what is available in Wikipedia. So in the example you see in the slide, Carnegie Mellon University has multiple attributes. So how it was called before in terms of former names, or I guess who established this school. It's established by Andrew Carnegie. This kind of structured data is available on DBpedia. And DBpedia database, as far as I know, is semi-automatically constructed, but also includes some human annotation to pick up more relational facts in Wikipedia page. Excuse me. And one other interesting things you can find in DBpedia is something you can see on the right side of the slide, where this Carnegie Mellon University entity has multiple ontology types defined by DBpedia ontology. So an example ontology type that Carnegie Mellon University is belonging to is educational institution, obviously, or organization, university. So if you go to the DBpedia website and maybe search ontology, you can see a big hierarchy of defined ontology, where you can see basically a mapping of each ontology type to Wikipedia articles. Another even larger scale database you can find from Wikimedia project is Wikidata, previously called Freebase. So some people might be familiar with the name Freebase. They are basically a curated database of entities. And unlike DBpedia, Wikidata's goal is to actually populate the data version of Wikipedia. So it's not like they are trying to render everything that is available in Wikipedia into a data format, but more like they'd like to construct the data version of Wikipedia. So basically they want to include not just the textual information or factual like triples, but also images that are assigned to entities. So you can find example images of, say, some birds in Wikidata birds page. So in the case of, yeah, this is an example. Most things you see here is pretty much similar to DBpedia, but as I said before, there's some additional metadata information that you can find for each entity. This is basically populated by community effort. I'm not sure how much semi-automatic construction is performed to Wikidata, but obviously there are a lot of missing entries, even though there should exist those entries. Say for person, there should always be when this person is born. It's not like if you don't have that relation, this person doesn't have a birth date, right? So yeah, so DBpedia, Wikidata are very popular, recently used explicit knowledge base. Do you have any questions until now? I don't know how to check, but.
So here are questions will be in the chat.
Okay.
Actually, we do have a question. Could you open the chat and read the question?
So the question is, it looks like DBpedia has more entities such as company or person names, but WordNet only have common words. Is that true? So WordNet, in my understanding, only have common words, and DBpedia focuses on, they do include company or person names, but they also include like basically any entities that you can find in Wikipedia. So I think Wikipedia also has a page for the number 1 or number 2, and that should also be in DBpedia. So that's kind of a common word, but they're registered in Wikipedia, so you should also find in DBpedia. So DBpedia is a like a superset of WordNet, I would say, but not necessarily superset, because some common words like function words might not be found in Wikipedia, and hence not in DBpedia. Sorry, I can't seem to find my own pointer, so let me try to close the, oh, okay, another questions. So if Wikipedia is mostly manually curated, does that mean it is much smaller in size than DBpedia? I don't exactly remember the number of entries in both knowledge base, but in terms of the data size, the last time I downloaded Wikidata dump was around, sorry, only triples dump was around 300 gigabytes. So it's pretty large, I'd say. So I think there's some involvement of automatic construction, or maybe downloading or dumping from Wikipedia directly some info box entries. But there are some parts of manual curation, and I think you can even make an account to register more entities, so register more relations between entities.
So let me add another comment, which is DBpedia, in a sense, is also manually curated, right? So it's extracted from Wikipedia, and Wikipedia is created by humans. So if I remember correctly, I think Wikidata is actually exporting some of the information from Wikipedia, like to seed the database. I'd have to go back and double check that, but I'm pretty sure that is the case. So you could almost view Wikidata as a superset of the data that's in Wikipedia, which is what went into DBpedia.
Cool. Are people looking at my Zoom group chat, I guess? Or no? Okay. Cool. Graham, could you stop me if you find any new questions? Because I don't.
I will, for sure. You might miss them if you're talking. So
okay. Cool. So next part, I'd like to talk about some popular methods for creating representations for knowledge bases. So as I said, knowledge bases mainly consist of entities and relations. So we'd like to represent them in some way so that the machines can featureize them. Yeah. So in 2013, I think still one of the most popular and simple method that people use is trans-E. Maybe you have heard of that name. The idea is pretty simple. So if you see the graph on the right, consider H and R, T representing subject, relation, and object, head, relation, tail. The idea is that if you have a triple H and R and T, the target entity should be represented as the sum of two representations, head representation and relation representations. So specifically, if it's in vector form, it will be like on the right side of the slide, where two vectors are combined together in an additive way to construct the target vector. How do you learn them? It's also pretty straightforward. Basically, what you want is you want to have the distance between the additive transformation head plus relation to the target entity to be closer if that triple actually exists, and to be further if that triple doesn't exist. So that comes to this margin-based loss, where you want to minimize the distance of the correct triples, but maximize the incorrect triples that I think you sample from. And such simple method, it's pretty effective. It's being used even until now, depending on the use cases. But there one big bottleneck, where this basically assumes that as long as you have the same head and same relation, that should point to the same point in the space, which means that they can't really handle one-to-many relations, where, let's say, Barack Obama has worked in some place, but he has obviously worked in multiple locations, like University of Chicago, maybe in Washington, DC, the city, or in the White House, whatever. Those three entities, target entities, will be mapped to similar point in space, which is not necessarily a good idea if we want to distinguish those three entities differently. So many to many, many to one, and one to many, these relationships are not modeled correctly or appropriately in this trans-E setting. So sorry, please forget about the mention of NTN. And there are a lot of methods, because of this simplicity, a lot of methods are following up this work by making the model more expressive, by, say, transforming the head and tail entity embeddings into a relation-aware way. So it will be like linear transformation of head based on the weight matrix, W, that is parameterized according to relation, something like that. But that leads to, but it's, a lot of advance in this knowledge-based representation learning has happened based on this trans-E embedding. And I'd like to introduce one example of the improved version of trans-E. So basically, this is proposed by one of the students at LTI, where the idea is to, instead of representing, instead of simply applying linear transformation on head and tail entity embeddings to make it more expressive or to make it relation aware, they define a set of concepts, which is latent. So you don't name which concept is attributed to what specific type of concept. But basically this D that you see in the equation represents weight tensor that is stacked as the number of concepts. I don't know if this conveys what I want to say. And basically what relation comes into play is that those concept matrices are linearly interpolated according to the attention vector that is dependent on the relation. So for some relations, maybe the concept zero weight matrix is used more heavily. while for another relation, maybe the final concept matrix is given higher weight. So the alpha times d, the linear interpolation of all the concept matrices, will be influenced by certain concept much more depending on the relation. After learning, sorry, this equation f of ht is basically the distance function of this d here. So you can substitute this d distance function with this f ht and do a similar kind of optimization. With proper regularization, the Xie et al. Authors found some interpretable phenomenon that is learned in concept to relationships. So some interesting things in from this heat map that you can see is on the 4 bottom rows. You see hypernym of tail and hyponym of head. So the bottommost one and the 4th from the bottom has pretty much the same heat map of attention of what concepts are used. And 2nd and 3rd last one, hypernym of head and hyponym of tail, which corresponds to the same thing. Sorry, but expressed in different relation. They are sharing the same, they're basically sharing the same concepts, some concept mixtures. So the main claim of this paper is to be able to reuse and share knowledge instead of modeling relations. Oops, maybe there's a question. Yeah, so to express again, so the heat map, each row corresponds to an attention distribution over the concept for that specific relation. So in the case of the bottommost one, if there's a hyponym of head relation, then the attentions are calculated against each concept matrix. In this case, I think there are 9 concept matrices. And yeah, the first concept matrix is used the most. So the 0 to 0.8 corresponds to the weight values, alpha. So the interesting thing is that the 0, 1, 2 concepts are used for hypernym and hyponym depending on the perspective, head and tail, and they are shared, which is an interesting observation. Any other question? I guess I can move forward. And a more modern way, more recently, other more complex models has been proposed, and one of the most famous and interesting architecture that was proposed is graph convolutional neural networks. Instead of, so far we have only been looking at triples, basically one head, one relation, one tail. But when learning entity embeddings or entity representations, why not consider all the local neighborhood if you can use them? So the idea is to use incoming local neighborhood entities. In the figure on the bottom right, you see the dark blue 4 nodes. Those are incoming edges to the current entity that we are interested in the red color, and influence or model the red node based on the incoming nodes, basically. So it's basically considering the many to one relations where the target is the one that you're currently updating the representations about. And how it works is basically you, the representation of the current node is computed by the weighted sum of linearly transformed the representation of the incoming nodes plus yourself, but in the previous stage. And this is performed recurrently. And if you perform recurrently, you can see that the coverage of nodes in the graph will increase step by step. You can almost kind of see, like in convolutional neural net, receptive field will increase if you stack the nodes, stack the layers up. So in theory, if you increase the number of layers of operations in this equation multiple times to like k times, you can capture k-hop neighbor nodes into the representation of your current node. Sorry, let me look at the question. For some reason, I can't get the Zoom. What is n in the? Oh, this math cal n. This is basically the neighbor. So what this means is that I'm looking at the ith node, and neighbor of I is such node, jth node, which corresponds to basically the incoming nodes. Yeah, and C here is normalization constant. So depending on the number of incoming edges, sorry, I need to do this. Depending on the number of incoming edges, this first term will be the absolute value of the first term will be varying, right? So they need to normalize them. And one of the examples of how to parameterize or how to represent C is basically the number of incoming edges. In this case, 4. Okay. Cool. So I've gone through some historical to more recent representation learning methods for entities. But to take a moment and talk about issues with knowledge base, which is basically the incompleteness. Previously, we talked about DBpedia or Wikipedia being partially manually curated. And as you can see, you can't really rely on humans to annotate 300 gigabytes of triples or even more. And according to some statistics in Freebase, or now Wikidata, 71% of humans don't have date of birth, even though they should have. And a lot of community interest goes to how to populate or how to automatically fill the knowledge base without relying on human effort. And so some tasks are called knowledge base completion, automatic knowledge base completion. And if the source of information is not the knowledge base, it's also called relation extraction, where you like to extract, literally extract relations from the text. So let me skip this because I forgot how to transition from this slide. I'll give you one example of actually knowledge-based completion using neural tensor networks. Basically, the idea is pretty simple. If you have 2 entity embeddings that you're interested in, you'd like to know if there exists any relations between the 2 entities or not. The equation-wise, it looks pretty simple. Now that we're all familiar with how neural models work, basically, it's a multi-layer perceptron that gives a score for a particular relation if there's any relation between the E1 and E2 in this equation. And Socher et al. In 2013 specifically proposed a network called neural tensor network. I've just read this paper, and to best explain this idea, it is basically that E1 and E2, you allow more rich interaction by parameterizing and interacting according to the tensors. So this WR1 to K term that you see in the first term of the second equation is interactions of two entities in the tensor space. So that understandably give more interactions than just the normal bilinear term. But one could argue that these are over-parameterized, especially considering how simple trans E is, and maybe the sum follow work, how simple they are, and they are pretty effective. So yeah, there has been some community effort on learning rich interactions of entities to find out whether relation exists between the two entities or not. And these are knowledge-based, this is the task of knowledge-based completions. And from now on, I'd like to shift focus a little more towards how those relations are learned or relations are extracted from text rather than using purely the knowledge base. And that connects to the previous knowledge base completion to this current relation extraction. So knowledge base are structured representation. They only contain the relationships between entities in a certain structured way, most commonly in graphs. But natural language text also contain a lot of relational facts, like maybe news text in the wild. So these learning knowledge from text directly is especially, in my opinion, called relation extraction. And researchers have focused on different ways, different paradigms to work on relation extraction. First of all, the number one thing that people have worked on is supervised relation extraction, where you basically have training set of this entity and that entity has relation. So Barack Obama, if the sentence is Barack Obama was born in the United States, then this entity Barack Obama and the entity United States have a relation of place of birth. And supervised data set basically construct gold labels for those entity pairs appearing in the same sentence, if it's a sentence level relation extraction. And the second paradigm is unsupervised relation extraction, which doesn't rely on label data. That tend to be pretty expensive to create, but all they can produce is span of entities. So in the case of Barack Obama, it would be a span of 2 words at the beginning of sentences, and the relation is expressed by the string that appears between the two entities. So if the sentence is Barack Obama is born in the United States, then the relation here will be something like was born in, something like that. So there is no attribution of set of relations that we're interested in because it's unsupervised. All you can do is to basically extract spans of entities and string of relation that lies between the entities. And the third one, which is the distant supervision. I took a long to come to this slides, but yeah, the third one is distant. I'm sorry, third one is not distant supervision. Third one is bootstrapping, where the idea is that you expand training data iteratively by first learning a model in one set of training data. You use that model to annotate more data in the wild and incorporate that into a new set of training data and combine together, perform this iteratively to expand the size of training data. But distant supervision is much simpler and it is shown effective. And the basic idea here is if we have some entity pairs of interest, in the case of Steven Spielberg and Saving Private Ryan, you go out and look for all the sentences that contain 2 entities. So you might get sentence number 1, like Steven Spielberg's film, Saving Private Ryan is loosely based on Brother's story. Or another sentence like Alison blah blah. You can actually see that first and second sentence both do not express the relation film director. The first one arguably, I mean, this can also be regarded as film director, but one could say this is film writer or film producer. The second one, some entity directed by some another entity can be misregarded as like CEO of. So LTI, formerly directed by the Dr. Jaime Carbonell. That's basically the head of the department relation. So sentences by themselves might not give correct labels or correct relations that we are currently looking for, but addition of these noisy but informative sentences helped featurizing what are the cues that connect the two entities that we're interested in. But this would still produce a lot of noisy but labeled text to train the system. Some examples of relation extraction or relation classifications are including LSTM-based recurrent model-based systems or convolutional neural net-based systems. I'll just go over one example of using CNNs. Historically, people used lexical features like dependency paths, or I think part of speech tags as well. But with the advancement of neural models, people started just modeling them over the, modeling the sentence over the, modeling sentence using some neural models that can take sequences input. In this case, CNN. They might include some other embeddings like positional features or features that encode or indicate entity positions, but otherwise mostly end-to-end models that can take sequence model, that can take sequences input, work pretty well in this relation extraction, supervised relation extraction task. Another interesting thing is not just using the text to perform relation extractions, but why not also take into account existing knowledge base? If we already have relational database, relational knowledge base. And this task, this work by Christina was to basically first find relations, quote by quote relations from the text by traversing the dependency path between the two entities in the same sentence. So for example, if there's a sentence of Bill Gates is the founder of Microsoft, then you can first run dependency parser and get a dependency tree. And obviously we know that Bill Gates and Microsoft are the two entities that we're interested. So we can go through the path in this dependency tree to construct things like this you see on the table. So subject connected by dependency edges leading to an object. So this kind of expresses the relation between two entities, two subject and object. And they modeled this with CNN by convoluting over this sequence of relation paths to construct the relation vector. So now that you have a relation vector and of course subject embedding and object embedding through the word embeddings, you can do the same optimization that you were doing before on knowledge bases, purely on knowledge base. In this work, they combined together text-based supervision that was constructed like this and a knowledge-based supervision in a multi-objective fashion. And they basically outperform in any single, outperform every single model by just incorporating textual supervision to this model. Finally, if we know that there's some noises in distant supervision, why not just model them as is? So the idea of this paper is pretty interesting and simple, but effective. The idea is if we know that the label training set contains some noise, the model will learn to transform their prediction into so that the prediction distribution would be similar to the noisy label distribution in the training set. So if you see the figure in the middle, what it does is sentences, first, number one, sentences are encoded into embeddings, and they go through this prediction architecture to get relation, basically softmax over relations. This is predicted distribution in the number two. If you have pure like gold training data that contain nothing but correct relation annotations, you can just take the 1 and 2 part and construct a relation extraction system. But if you expand the training set using distant supervision, those expanded training data set contain some label noise. So you would like to transform the predicted relations using transition matrix to match the observed distribution. And the question is, in the previous work, what does the CNN take as input and produce as output? The previous work I just described take word embeddings as input and produce, oh, sorry, this one. Yeah, this one produce, take as input embeddings of those paths, if I remember correctly. So subject and edge or the co-founder, those things, every single of them has embeddings. And the output will not be probability distribution or anything like that. It will be a vector that is representing the relation, which is described by a certain path. So textual pattern you see in the middle of the slide here. Each of them is potentially a relation, and what they wanted to do is to express this in basically featureize this relation into a relation vector form. They use CNN they run CNN over the sequence of path specifications, and finally form a relation vector for each of this textual pattern. And once you have each of the textual pattern, you can basically construct a training example of Bill Gates, this relation vector, and Microsoft. And Bill Gates and Microsoft, you can also instantiate as entity embeddings. So it reduces to the same setting as knowledge base representation learning setup, where you have entity embedding and relation embedding and target entity embedding. Okay, cool. So yeah, so what this work tried to do is to basically model transition matrix that transform the relation prediction distribution, if given only the pure training data that is like correctly labeled, into a labeled but noisy training set. So they regulate transition matrix in two ways. The first way they try to do is to do a trick called trace normalization, which is basically which controls how much predicted distribution how much noise do we model in this transformation from number 2 to number 4 distribution. So if the observed distribution is also the gold distribution, then there shouldn't be mislabeling problem where the correct label is label number 1, but are mislabeled to number 2 and number 3. In this case, the transition matrix should be identity matrix, where the correct label should always go to the correct label. However, if there are some noises, then there are some cases that correct label goes to a wrong label, so we have to model them. And trace normalization, trace regularization controls how much mislabeling noise we consider. Another thing is, as I previously described, the first module, second module, encoder prediction module, first part, can be trained beforehand without looking at distant supervision expanded training set. So if you already have some more reliable data, like goal data, then you can pre-train encoder and the prediction module first, and then train the noise modeling part and the transformation part using the distantly supervised, less reliable data set. And finally, I'd like to go over a little bit of how we can use knowledge base into downstream tasks for using neural models. This is rather a representational learning rather than downstream tasks. But this is, I think, outstanding paper award from 2015. What they do is basically, if we are given any pre-trained embeddings, word embeddings like glove, back in the days, glove or word to back, and we have some knowledge base, in this case, WordNet, we like to adjust the pre-trained word embeddings in a way that it respects the knowledge base, where the kind of respect that I'm talking about is if the two nodes are connected, in the case of WordNet, it will be like car and motor vehicle, then the representation of two embeddings should be tied closer together. So if you see the objective function on the bottom side of the slide, you see two terms. The first term is to reduce unnecessary movement of the word embedding as much as possible. So QI is the original embedding. Q hat I is the original embedding, and the new definition of the same embedding after adjustment happens, the distance between them should be similar should be smaller. So you don't want unnecessary post hoc calibration, too much of them happening. At the same time, what we also want is that if there exists an edge between two nodes, nodes are in this case represented I and J. So node I and node J are connected. Then we'd like to minimize distance between the representation of the two nodes. So QI is the word embedding of some words like car, and QJ is word embedding of motor vehicle. They want to make it close together. And alpha I, beta ij are the hyperparameters. So this idea basically can take any word, pre-train any embeddings, and potentially any knowledge base, any graph-based knowledge base. I personally have experimented with ConceptNet or other knowledge bases, wasn't that helpful. But in their work, they use WordNet, which I think makes sense to put synonyms, or is a part of closer relationships, closer relationship words into a similar word embedding point in the space. Some follow-up work also experimented different type of relations like antonyms. Another work is if we have some knowledge base, so this is our work, but if we have some knowledge base, and knowledge base is basically considering explicit knowledge base, they are a repository of a lot of real world entities, or real world entities. And why don't we use them for natural language generation or language modeling? Because a lot of issues with the existing language generation models is that they are not really good at generating the real world entities or factual relations in a sentence, like Barack Obama was born in the United States, for example. So our idea is to provide language model with some snippet of knowledge graph, which is some subgraph of knowledge graph, and taken from Wikidata, and allow the model to copy at a certain point, so that the generated sentence would look more factually natural. what you can see is in the graph, in the figure below, suppose you have a target, generated text, Barack Hussein Obama II, born August 4th, comma 1961. I think state-of-the-art pre-trained language models is not capable of generating his birthday exactly as is. But if you already have some knowledge base or knowledge about birth date of Barack Obama, then why not use them and fill the these full words by copying them from the knowledge base. Yeah, so not limited to my own work, but there are also different works that try to incorporate knowledge base into language generation. There's also a task of data to text generation models where the way the task is to verbalize the knowledge base into descriptive text format. So a lot of natural language generation tasks are also connected to, are also trying to incorporate knowledge base into account. Finally, sorry, a question is, so yeah, the question is how the model is trained. So if you remember how the language model is trained, sorry, excuse me. If you remember how the language model is trained, the language model is trained by maximizing the likelihood of the sentence, marginal likelihood of the sentence. And they are, that is decomposed into, you know, chain rules and etc. In this case, what we do is, if you look at the figure here, and suppose this is the whole sentence until 1961, there's a way to generate this sentence. One way is to just keep generating word by word. Barack Hussein Obama II, born August 4, 1961. And that would be taking the edges in the bottom side. Sorry, I can't, maybe I can try putting some pointer. No, sorry. Or another way of generating this sentence is to not use the word, but skip and say, I want to generate a birth name, and then fill from the knowledge base, Barack Hussein Obama II. Followed by born, maybe I'll use the word because there's no knowledge base entries about born, and followed by the birth date. Instead of generating word by word from the vocabulary, I will just decide to pick this relation birth date of Barack Obama and let the rest of the 4 tokens filled by the knowledge base entry. So basically from the first node, the leftmost node to the rightmost node, there are different paths you can go to express how the generation process is, to express the generation process. And we will marginalize over all the possible generation processes. So you can take word-based prediction at the beginning of the sentence, like talk about Barack Obama word by word, and later move on to the copy-based generation or vice versa. And by marginalizing over all possible generation paths, you can leave out this latent path and follow the marginal likelihood of this sequence, P of X. And we maximize over that, maximize this quantity, basically. Yeah, for more information, I guess I can talk about that the day after tomorrow if you come to office hour. Okay, so yeah, finally, cool. We, in the beginning of the lecture, we talked about use of knowledge base for QA. There's actually a big community of KV QA or knowledge-based QA where question answering is happening over the knowledge base, the structured data knowledge base. But this work is the most recent work from iClear, where they tried to do open domain QA, where the QA resource that they have is a full corpus of textual corpora. And this work is pretending this textual corpora as if it's a knowledge base. So the definition of knowledge base, according to the previous slides, is that we have some entities and relations, and they are in the structured connections. But in this case, I think the definition is more like if we query with query the knowledge base with head entity with a certain relation, we want some tail entity or target entity back. And the core challenge of doing knowledge or treating text corpora as knowledge base is that while the knowledge base has always been operating over the entity, it's never be mentions of the entities. So there's this distinction of entity and dimensions where Barack Obama entity can be expressed in different ways. Barack or Obama or Barack Hussein Obama II. So there's basically one-to-many mapping of entity to mentions. And in natural language text, there's always, entities are always instantiated as mentions, one of the mentions. So if you want to query over the textual corpora, you have to match your query in mention zone or mention space. So what they do, the figure may look a little complicated, but if you look from the top through the highlighted rectangle earlier, you will be like, first you have question. When was the Grateful Dead and Bob Dylan album released? From here, you first link the entities or run an NER and run the entity linker to get Grateful Dead and Bob Dylan entity. And then you will go through this squared zone to convert this entity vector into mention vector by transforming them using this specific matrix to construct mention vector. Please go over the paper if you want like most details about this. The basic idea is to first construct mention vector from the entity vector. And this matrix, A from E to M, highlighted matrix, entity to mention, is basically the TF-IDF value between an entity and specific mention. Next, what you do is to also bring this entity vector that you see at Z0 and bring that in query pre-train go over the textual corpora and collect all the sentences that contain specific entity of interest. In this case, we're interested in the Grateful Dead and Bob Dylan. So we have a bunch of sentences that contain Bob Dylan or Grateful Dead, as you see in the bottom of the figure context. And then since we are also feeding the questions into this F of M model, pre-trained model, they will, using these features, they try to rank this context sentences retrieved from the textual corpora in a way that is most relevant to the questions that currently model is asked. After that, they would also aggregate and construct, construct vectors from the retrieved relevant context found in textual corpora. And finally, in the colored orange area, you combine and compare the mention vector constructed in the first step and the retrieved vector constructed in the second step and get relevant mention scores. And using those relevant mention scores, you construct it back into entity vector, as you see in the highlighted square zone, to finally get which entities have higher scores than others. I forgot to mention that Z0, the first entity vector, the very first step, Z0 is a one hot vector. So Grateful Dead and Bob Dylan is turned on, rest of them turned off. But after going through these processes, you get score values, and you use these scores if you want to go over the second step. So second hop edge, dashed edge will go over to Z0 again, and they are now as many times as you want, iterate this process to construct mention vector, retrieve relevant mentions, combine them together to compare, get more probable entity distribution that you might think that some of them might answer the questions until you get the correct, until you get, yeah, as many times as you want. Sorry if the explanation was a bit rough. But yeah, that's the overview of this work. And the interesting part of this work is that they operate knowledge-based querying in mention space rather than in entity space, because you just can't do in entity space, because entity linking itself is a bit noisy, or entity linking doesn't operate perfectly. So yeah, that concludes my part of the talk, and I'll hand over to Graham for the rest of the lecture.
Hi.
Yeah.
So I'm happy to turn over. Are there any questions about Hiro's part while we switch over the share screen? I guess not. So I will, hang on 1 second. Just want to make sure I have my chat open. Okay. So I'll turn over to my part. I'm going to talk about schema-free extraction. I might not have time to get through all the slides, but I think that's okay. I think the earlier part that Hiro covered is probably the more important part. But basically, schema-free extraction, in contrast to the relation extraction that we've done so far, means that we want to extract information in the knowledge base where the knowledge base structure or the relations specified in the knowledge base are not specified beforehand. So the basic idea behind open information extraction, which is one example of the schema-free extraction, is that the text is the relation. So for example, United has a hub in Chicago, which is the headquarters of United Continental Holdings. We would extract things like United has hub in Chicago. Chicago is headquarters of United Continental Holdings, etc. So here the relations are has hub in and is the headquarters of. So the nice thing about this is we don't need to specify a priori which relations we're interested in. However, it makes it difficult to abstract. For example, if we had United Continental Holdings has its headquarters in Chicago, that would mean virtually the same thing as the second example here, but they wouldn't be able to be easily decided to be the same piece of information, unlike a regular relation extraction system. So a lot of work on OpenIE has been rule-based. So some examples of this are TextRunner and Reverb. And basically what they do is they use a parser to extract these relations according to rules. So some examples could be a relation must contain a predicate, a subject, and the subject and object must be noun phrases. So this ensures that you get kind of like reasonable looking relations. And in some cases, at least in these papers in 2007 and 2011, one really important part was that they wanted to run this on the whole web because they wanted to extract, information from the whole web. And in order to do so, basically, at that time, parsers were not fast enough to run the parser over the entire web. So they would take the parser, parse a small amount of data, and then train a much faster sequence labeling model or something like that to parse large amounts of data. Arguably now, the parsers have gotten quite a bit faster, so it might be possible to just do this without worrying about it. So I got a question. Are parsers always required to do OpenIE? And that's definitely not the case. So I think I'll have a couple examples in the next part. So another thing is they will often aggregate multiple pieces of evidence in some sort of heuristic way to find common and potentially reliable extractions. So, you know, if something is only said once over the entire web, it might not be super reliable. But if something is said many times over multiple sites, over sites that you trust relatively much compared to other sites, then that's a good sign. So there's also neural models for OpenIE, and these are examples that don't need a parser. So unfortunately, heuristics are still not perfect. And you might extract a lot of things that don't intuitively look like relations. And as an interesting example of how we could create data to instead train a supervised model that would potentially be more accurate, Hood, all 2015, basically came up with questions that you could ask crowd workers to try to extract particular types of semantic role labeling relations. So for example, we have UCD finished the 2006 championship as Dublin champions by beating St. Vincent in the finals. And you have a bunch of questions like who finished something, what did someone finish, what did someone finish something as, etc. And this allows you to extract kind of predicates and arguments for arguments for particular predicates. And this can be converted into OpenIE style extractions for use in a supervised tagger. So an example of this is Stanovsky et al. And they have some rules to take these manually created semantic roles and convert them into OpenIE extractions. So if you're interested in this, I'd definitely take a look here. This can be useful if you want kind of a quick, a quick approximation to a full relation extraction system for a new domain. So that, any variety of OpenIE, not just neural OpenIE, but this is potentially something that you could take a look at. So another interesting method for learning about relations is to learn relations from relations. And the basic idea is that if particular relations hold, it's very likely that other relations hold. So to give an example of this, let's say for my example, employer Carnegie Mellon University. My employer is Carnegie Mellon University, and that makes it very likely that my current place of residence is Pittsburgh. So even if that place of residence was not annotated in a data set, we might be able to infer that from the fact that the location of my employer is Pittsburgh. So we can contrast between modeling word embeddings and modeling relations. So word embeddings give information of the word in context, which can be indicative of KB traits. So word embeddings, or I could also say entity embeddings. And also relations or combinations thereof are also indicative. And that's what I said before, but basically this can also be considered a link prediction problem in a graph. So we have entities as nodes of the graph and edges between the entities as edges in the graph. And we would like to fill in the edges that we don't know based on the other ones we know. So for one example of how you could do this, this is a paper by Sutskever et al. 2009. So interestingly, this is what Ilya Sutskever did before making sequence models or other things like that. And basically the idea is that you can model relations by decomposing a tensor containing entity relation entity tuples. So if you have a tuple of entities and a tuple of relations and a tuple of entities, basically this gives you a three-dimensional tensor. And you can do a low rank approximation of this tensor, and then feed in this low rank approximation to try to complete the other parts of the tensor that have not been filled in explicitly in the knowledge base. So this is relatively simple. I think the main difficulty here is computational considerations, but I think that's not super core to the discussion here. So if you're interested, of course, you can take a look and see how you can do this over large knowledge bases. But another implication for this type of method is that we have been talking about both schema-based and OpenIE extraction. So essentially relations that are specified according to a schema and relations that are specified using OpenIE, where you have text that doesn't abstract. And because of this, Riedel et al. 2013 proposed an idea called universal schema, where basically we embed relations from multiple schemas in the same space. So to give an example of this, we have OpenIE extractions on the left side here. And then we have freebase extractions, which might be from one particular schema. And then we also have TAC extractions, which might be from some other schema. And by doing this, basically, we can put all of these together into one big tensor. And once we put them together in one big tensor, we can then do matrix completion and try to fill in the missing spaces. So why is this good? The reason why this is good is because OpenIE extractions are extremely easy to get from large textual corpora online, right? So we just parse a huge corpus. We extract information from there, but nonetheless, because these things don't abstract to each other, we would like maybe a more abstract version of a relation like that provided in freebase, so we can fill these in using all the information that we found online. And we can also do so in a probabilistic way if we would like. So another example that I kind of alluded to when I was motivating these methods is modeling relation paths. So multi-step paths can be informative for indicating individual relations. So there's an example from this paper, which is given a word, recommend a venue in which to publish the paper. So we have a paper that we would like to, publish somewhere. We have an interesting research idea, and we would like to know the most appropriate venue to publish this paper in. And so basically what they did in this paper was they extracted paths, like word has title -1 to paper. So basically this is saying the word is in the title of the paper, and then that paper is in a journal. So this is a path that's very indicative of what journal a paper was going to be in. Another example would be a word in the title of the paper, and then we have a first author of that paper. That first author is an author of another paper, and then that paper is published in a journal. And now this path is a little bit more indirect. It's basically saying that if that author has published somewhere, that might be a good choice. But nonetheless, it's indicative. So you basically have this path as well, and then you can give it a separate weight, a smaller weight than the top one, but still a relatively high weight. So then you can combine all of these paths together and score the output journals here and see, like what you could, which one would be the best choice. So there's also, we talked a little bit about like trans-E embeddings or other things like this. There's also been work that explicitly attempts to optimize these relational embeddings over paths. So one of the problems with using paths not in an explicit knowledge base that's been curated or something like this, but in embedding space, is that traveling over relations might result in error propagation. So in your first step through an embedding space on a relation path, you might make a mistake, and then all the other embeddings downstream would also be poor. So instead, we use a simple idea, which is that we optimize the relation embeddings so that after traveling along a path, we can still get to the correct entity. So to give an example here, we have a question about where Tad Lincoln's parents were located. And so what you do is you follow the parent relation, and then you follow the location relation. And you explicitly optimize the model so that after following this path, you get the correct answer, like Springfield, for example. And interestingly, this method of learning relation embeddings actually does better than just the one-hop method for optimizing relation embeddings like TransE. And it does better even on one-hop relations. And the basic idea is that by giving it a bit more information from all the different paths that you could be traveling on, as opposed to just the one-hop relation, it makes it provides basically a stronger learning signal. So I think this is an interesting paper if you're interested in the idea of relations. And also, there's an idea of differentiable logic rules. So basically, it considers whole paths of logic in a differentiable framework. So the idea is that we have essentially has office in country as a big logic rule, and then this can be split up into has office in city and city and country. And in order to come up with this, they basically treat the path as a sequence of matrix multiplies, where we have this matrix, we have this matrix M here. So we multiply this matrix M into some sort of embedding that we have to represent the original entity. And we then will follow a path, much like I talked about in the previous time. But each of these logic rules, instead of being a fixed, modification to the embedding, it's given a particular weight for each of the rules that we apply. And because of this, it's kind of a combination of these two previous ideas. We have the optimizing relation embeddings over paths, and then we also have the modeling relation paths with weighted rules, essentially. And this method kind of gets both of those together in a single framework, which I think is interesting if you want to consider kind of multi-hop reasoning along knowledge graphs. So that is all we have for today. We don't have a huge amount of time, but I could take one or two quick questions if there are any.